what do we know about how we proceed with this?
You can do global bracket.
Okay, can't synthetic division?
Yeah.
Can we do synthetic division?
Yes.
Yes. No.
Yes, you can.
No, how come? You're right, we can't. Why not?
Because you were
X
skeptical.
squared?
Yes.
Oh, okay, my reaction.
Because why?
You can't use synthetic division because there's an x squared there. Okay? So we have to use polynomial long division on this one. We don't have a choice. Okay, now which one, when we set up our polynomial long division though, what goes where? What goes inside and what goes outside the division? Good. Numerator goes in, denominator goes out, right? So, okay, now tell me what I need to write under here. Be very specific, please.
5x plus 14x cubed plus 9x.
Okay.
He's secretly random.
We're missing something.
Plus 9x.
Okay.
Plus
Zero.
0x.
Okay. Okay, because remember what we said last week. We want to have a column. When we go through the long division process, we're going to keep on developing these. We're going to figure out how many times the leading term goes into the leading term and then distribute that number all the way through. And then we're just going to repeatedly be subtracting terms as we look ahead. So we have to have a column for each power of x then, right? Because we don't know where, even though we don't have an x squared or a 0 in our numerator, that doesn't mean that we're not going to be subtracting polynomials with x squareds and constants in them. So we got to have a place to put those, right? All right, so now, first things first. How do we know what our first term of our answer is? What do we do?
What did you just say?
We want to compare the leading terms, right?
Yeah.
And I want to ask the question, how many times does the leading term on the bottom or outside divide into the leading term on top, which is inside?
Twice.
Well, okay, not just twice. Now, there's two parts to this. There's a number part and a power of x part. A better way to think about this maybe is to ask yourself the question, x squared times what is 5x to the fourth?
5x squared.
5x squared, okay. Okay, and now what? Okay, so that's our first part of the answer. What do I do with that? Okay, remember, here's where I distribute that, right, to both terms. Remember that? Whenever I get a number up here on top, I immediately distribute it, and then I'll subtract the result. Okay, so what do we get when we distribute? Well, we get, let's see, 5x squared times x squared is our 5x to the fourth. We knew we were going to get that one. 5x squared times 3x is what? 15x cubed. So we line it up in the x cubed column. And we're going to subtract the whole thing. Okay, so we're going to subtract each term from the term above. 5x to the fourth minus 5x to the fourth cancels. We knew that was going to happen. That's why we picked 5x squared, right? What's 14x cubed minus 15x cubed? Negative 1x cubed, or just negative x cubed. And what do I do with the rest of the terms? Bring them down. Bring them down. Because I'm just subtracting 0 from them. Right, there's nothing to subtract. So plus 0x squared plus 9x plus 0. Okay, what's next? Okay, x squared times what is negative x cubed? Negative x. Okay, so the next term is negative x, and we'll go ahead and distribute that to both parts. Right? Okay, and if we do that, what is 5x squared times times x squared? I'm sorry, negative x times x squared. Said that wrong.
Negative x cubed.
There's our negative x cubed. Negative x times 3x is good, negative 3x squared, and we're subtracting the whole thing, right? So the x cubes cancel. Now what's, you got to really pay attention to this one. What is 0x squared? So just 0 minus negative 3x squared.
3x squared.
Positive 3x squared. And then we'll bring the other stuff down. Okay, x squared times what is 3x squared now? 3, so that's our next term. And if I distribute the 3, good. 3x squared plus 9x. And then I'm subtracting the whole thing. And what do I get? 0. Well, that's my remainder. Then I have, my remainder is 0. There is no remainder, right? So what that tells me then, now I want you tell me, what does that mean? If I were to take numbers as an example, if I divide...
It means it divided equally.
Yeah, good. If I divide 12 by 3, what is that equal to? 4.
No remainder.
Okay, 4 with no remainder. So that tells me then that 3 times 4 equals 12, doesn't it? Okay? So there's two important things we could say about that. Two of the things that we've said in the past, many times, is that 3 divides evenly into 12, but also that 3 is a factor of 12 then, because it divides evenly in there, right? Okay. So going back to this previous page then, because there's no remainder, then that means that my answer up here is just a straight 5x squared minus x plus 3 with no remainder, right? So in other words then, if 5x to the fourth plus 14x cubed plus 9x divided by the quantity by this polynomial x squared plus 3x equals this polynomial, if we kind of color code this, so we got a red one, a green one, and a blue one, then isn't the green times the blue equal to the red, right? If I multiply both sides by the green polynomial, right? Okay, so what we did there, we did division, but it just so happens that because there was no remainder, we ended up factoring the numerator, didn't we? We killed two birds with one stone here. We know that this is our answer, but we also know, we take this result, okay, so everybody agree? Yes. Everybody agree?
Yes.
Okay, so that allowed us to factor that. All right. Okay, another one. Okay, how about that guy? Okay. Now here's what I want to do with this. I want to review synthetic division a little bit. Okay, but I want to remind you about something with synthetic division. Remember that we did some stuff with synthetic division earlier that we called synthetic substitution. Okay. Let me. Oops. Okay, good. Okay, so Remember what we did with synthetic substitution. What if I want to know, for example, what if I want to know the value of the function at 0? If I want to plug in x equals 0. Or better, let's do it instead. What if I want to plug in 3? If I want to plug in 3, I want to know what is f of 3. What's the value of the function when x equals 3? We did some of this stuff in 6.1 or 2, I can't remember which section. What did we do with this?
We put in our calculator.
Okay, we put in all the coefficients. And your calculator won't help. Well, in this case it will, but it won't help you real soon. It won't do you any good. Okay, we put in the coefficients, including 0 coefficients, in descending order. So what are they? 1,
0,
0,
-2,
0,
-11,
Zero.
because we're missing the x to the 5th and the x cubed and the x to the 1, right? So we got to put zeros in there. We got to have a column for every power of x, just like with long division. Okay. And so if we put the 3 down here, we can just go through. You tell me what to. Yeah.
I thought it was -3.
No. That's for synthetic division. But now, whatever the value of x that we're plugging in, that's the number that goes out in front for synthetic substitution.
Oh,
The substitution. Okay, so now we'll bring the 1 down. What goes here?
3,
Here?
3,
9,
Good.
7, 21, 21, 63.
Yeah.
52.
And then, what's 3 times 150?
Oh, okay.
450. What's 3 times 6?
348.
Okay, so then it'd be 450 plus 18.
Plus 68.
Yep. Plus.
What's that? 480.
Yeah. Okay, so that tells us that the y value, when x equals 3, the y value is 480. Okay? Yeah. Now, what does it mean? What does it mean to be the 0 of a function? What's it mean to be the 0 of a function? So, for example, let's take this function. We've got, how about f of x equals x squared minus x minus 2. If I want to find the zeros of the function, what am I doing? Those are the x values that do what?
They hit the line.
Yeah, they hit the x-axis, which means they make y equal to 0, right? Okay, those are the values of x that are going to make the whole thing, which is equal to y, be 0, right?
Yeah, sure enough.
Okay, so when we ask for it, now that's, make sure you got to know that, because from here on out, half the questions are going to ask you about this stuff. Did everybody get that?
Yeah.
When they're asking for the zeros of a function, we want to know the values of x or t or whatever the independent variable is, usually x, the values of x that are going to make this thing 0. So to find them, we would just set the function equal to 0 and solve, right? Okay, so that's what we did. We set this equal to 0, and now we're going to solve, right? Okay, well, go back to chapter 5 for a second here. What do we do with this in chapter 5? We have a quadratic equation in standard form, so we always have the option of quadratic formula, right? But we don't need to here. Does this factor? Yeah, so I'm going to have a -2 and +1. Multiply to -2 and add to -1. So there are magic numbers that work here. Right? X plus 1 and x minus 2. And so then once we've got this broken down, now that we've traded two small, a product of two small equations for one big one, or expression, we can, by setting these equal to 0, we can find the solutions to this equation, which are the zeros, right? Much more easily. Now I want you to notice something. Everybody watch very closely for a second. This will stick in your brain if you really watch this. I want you to see something very important. When I set these equal to 0, when I set this x plus 1, what do I get for my answer? Okay, so that's one solution. Or, what about this one here? X minus 2 equals 0, so x equals 2. Okay, now I want you to see something. I want you to see something. I want you to see that this 0 right here, x equals negative 1, came from the factor x plus 1. And the factor, and the 0 x equals 2 came with the factor x minus 2. Makes sense, doesn't it? Because the factor that goes with a 0 must be the one that you had to set equal to 0 to get the answer, right? So I want you to just practice a couple of these. We're going to focus just on this one little relationship for just a second. I'm going to give you a factor, and you tell me the 0. Don't say anything out loud. So here's the factor.
Negative 1.
0, x equals negative 11. Okay, this time the factor is going to be whoops. What is it? Yeah, because if I set that equal to 0, I subtract 1 and divide by 2. Right? Okay, what's my pattern then? What if I want to reverse the process? This time I'm going to give you a 0 and you tell me the factor. The 0 is x equals 3. What's the factor? Good. The 0 is... What's that? Oh yeah, absolutely. But there's only one factor for each 0. Each 0 is tied to a single factor. What about this one? What if we have x equals negative 2? X plus 2, which is the same thing as x minus negative 2, right? So it's easy. If we want to get the factor, all we're doing is just subtracting the 0 from x. Now here's one that's here's my bonus one. What about this?
2x minus
Okay. Yeah, it's x minus 1/2, but if I want to clear the fractions there, right, that's the same thing. If this is what's equal to 0, right, to get that, if I multiply both sides by 2, multiplying 0 by 2 doesn't change it, does it? If I multiply both sides by 2, I get 2x minus 1 equals 0. So there's the factor. But we're not even going to do that in this chapter, so that's not even important. If you can do this, you got it. Okay? All right, so now going back here. Here's what I want you to see. Okay, now we made a correlation here, right? We said that the zeros of a function are the values of x that make y equal to 0, right? Synthetic division and synthetic substitution are the same thing. We just interpret the results differently, right? So if I want to, I'm going to give you a list of possible zeros here, and I want you to determine which of those work. Now, what would be the easiest way to check? Plugging them in synthetically, right? We could run these through synthetically. I could make a synthetic bracket, and we'll put we've already done this, right? That was a 1, a 0, a negative 2, a 0, 11, 0, and 12. And if these are going to be zeros, what has to be the number in the remainder box? 0. Yeah. If I get a 0 back, then they check off, right? Okay, so let's see. Let's just try them out. Let's start with
Negative 11.
negative 11. Yeah, I did that last time too. Negative 11. Okay, so let's start off with, we'll just arbitrarily say we'll start off with negative 2, how about? Actually, let's start with the easy ones. Let's start with the ones. Let's put a negative 1 out there. And then what's down here?
Negative 1.
Negative 1. 11.
Negative 1 works.
Negative 1 worked.
Negative 66.
Okay, now I want you to see something here. So that tells us it worked. What does that also tell us about division? If I divide the polynomial, everybody watch this please. This is big. If you can get this now, you'll have it. Even if you momentarily forget it, it's all in your brain and it'll come back. If I divide this big polynomial, this big 6th degree polynomial, now what's the factor that goes with the 0 minus 1? X minus negative 1, so x plus 1. If I divide by the factor x plus 1, I get this polynomial with no remainder. Right, now remember that this is, when we think about this as division instead of just substitution, these numbers out here are actually every bit as important, if not more important, than what's in the remainder box, right? Remember what that told us? That told us that this was our constant. Why is that not? What's going on? Oh, there we go. Okay.
What's an X?
So that's a plus. That's an x, right? This is an x squared. That's an x cubed. That's an x to the 4th. And that's an x to the 5th, right? And I'm just adding all those terms up. Agreed? So then doesn't that tell me that this polynomial, this big one, times x plus 1 equals that?
Yeah.
So in finding a 0, we actually also found a factor, right? Okay, but now if we want to keep going with this, we found one of them. Now, the next step, I guess, would be to just start over again, to take these and make a new synthetic division problem. Watch this. Done. There it is. Right? We'll just nest our synthetic division, so now we've got a smaller one to deal with, right? And our remainder box just moves over to there.
So what are we putting with the...
Okay, good. So now we tried negative 1 and it worked. But here's my question. You asked a good question earlier. Could there be multiple, well, maybe this is what you asked, but I'm going to pretend it was. Could a 0 be a factor more than once? Yeah, it could. So in other words, negative 1 might work again. So let's find out. Let's try it again. So I'll put negative 1 in again, and either it's going to work or it's not.
Are we going to go to the lab today?
I kind of doubt it. Doesn't look like it does. Why is this thing not? Well, it's working now, I guess. Okay, so let's try this. If I bring the 1 down, oops, positive 1. So it didn't work, did it? Okay, so negative 1, it worked once, but that was it. Okay, so we'll go back and we undo all that stuff.
Why were you doing that?
Because I wanted to see if negative 1 was a double 0, and it wasn't. So let's go ahead and cross it off the list. Negative 1, it worked once for us, but now it's gone. Okay. Well, let's try the next easiest one would just be positive 1, right? So let's try that. What do I get here? 1.
0.
I think this is going to work out really well.
0. 0. 0. It works.
Worked. So 1
I see a pattern.
worked. Okay. Yeah, there is kind of a pattern, isn't there? So 1 worked, and now we can start again. Go down to the next layer. Okay, well, I don't know. Does 1 work again? Let's see. 1, 1. Tell me when you know it does or doesn't.
No.
It's not going to work, is it? Not going to work. Okay, so we can cross 1 off the list, and let's try negative 2.
So the number will always work for every single one of these or what?
No, so far they all have, but when I give these to you on the test and on your homework, from the list, some of them will work and some won't.
Wait,
Yeah.
so you don't have to start all
So what's our answer?
We're not done. We're not done.
We have to do all of this?
Is there any number that'll just go through it every time people will have a zero as their negative?
Well, yeah, it could. It's unlikely. I'll make one up for you here. It's not today. Well, I'll make one up for you. Okay, so let's try -2. Winner. Okay.
And that's 122.
Okay. Now I want you to notice something. Now, look at the polynomial. I want you to look ahead here a little bit. When can we stop this foolishness?
Never.
Well, we actually could even stop right now if you saw it. Right now, look at the polynomial that I've got left down here. -6. I've got a plus 3x. I've got a -2x squared and an x cubed. Right? Notice that these polynomials have gotten progressively smaller. In fact, we've whittled them down by a power each time we've run through the synthetic process, right? Now, at some point, we're going to be able to just take this polynomial. If we had set this first one equal to 0, it's not helping us. We don't know the answer to that, right? See what I'm saying? The first one, it wasn't going to help us. We don't have a magic 6-degree polynomial formula like we have a quadratic formula. Okay? We could not have solved this polynomial equation. But at some point, we're going to get a polynomial that we can set equal to 0 and solve. Where's that always going to be? Can I set this one equal to 0 and solve? X cubed minus 2x squared plus 3x minus 6 equals 0? We actually could, but it's an accident that we can't. Normally, we can't. We can't depend on being able to solve a quadratic, but when it's squared, when it gets down to quadratic, when I get down to having 3 numbers down here, then I can just stop and plug them into the quadratic formula if I want to, right? We're not quite there yet. 2. Okay, so the suggestion is let's try 2. Okay?
So we have to try -2 again?
Well, we probably should. Yeah.
But
Let's see if it
okay,
works.
we'll try 2 then.
Let's just try it real quick. So bring down the 1. I'm going to get -2, -4, +8. It's not going to work, is it? Not going to work. So -2 doesn't work.
So 2 has to work.
We can cross -2 off. Well, it doesn't have to.
Yes, it does. You number left.
But who's to say any of those work?
Well,
I mean, we just happen. But maybe the zeros could have been like 3, 5, 7, and 4 or something, right? It just happens that some of them work. 2 may or may not work. Anybody, any bets? It's going to work? Okay. 1.
So,
So it worked.
Let's do it again.
Okay. And now, so they all worked, and we could do it again. But let's just say now that what we were trying to do, let's say we were trying to find all of the real zeros of that original polynomial. Okay? Are you with me? The zero, well, that's what we found. The zeros are the numbers that divide in evenly, right? Like these did. Okay? Factors that divide in evenly, right? The zeros are associated with factors of the polynomial. Good. Okay, now, if we wanted to find all of the zeros, we have found 4 of them. All of these numbers have worked. -2, -1, 1, and 2 are all real zeros. Now we've got it down to the point where, look, we've got a quadratic expression left. I've got x squared plus 0x plus 3, right? Those are my coefficients, constant x, x squared. So I could take that quadratic equation, 1x squared plus 0x plus 3 equals 0, and just solve it. Go back to chapter 5 stuff. Now, what's the easiest way to solve this equation? What do I do here? How many x's are there up there? Well, it's squared, but there's a single x I can point to so I can isolate it. What are the 2 steps I go through to isolate it? Good. Subtract 3. Good.
Plus or minus.
Good. Plus or minus I. right 3. Okay? So those are imaginary. So those wouldn't count. We only had 4 reals and 2 imaginaries. If we had wanted to find the imaginaries, we found them. Okay? Now, it might seem pretty arbitrary that I gave you those possible zeros, a list of them. Did I have to do that?
No.
Not necessarily. There's a rule. Now, I'm not going to spend a lot of time on this rule, but here's the rule. If I take this polynomial and I want to know what the possible fractional or rational zeros are, here's how you can always find out. This is called the rational root theorem. What is this thing? My pen is not working well.
You messed up. Try it again.
Let's try that. I think it's finally.
You don't succeed, try it again.
Okay, so what was I doing? What did I just ask? What did I say I was going to tell you? I lost my train of thought. Oh, yeah. Okay, I gave you a list. But how could we have maybe known a list to draw from? Here's the rule. The rational zeros, and when I say a rational number, what do I mean again? Going clear back to pre-algebra. What's a rational number? Say it again. Okay, yeah, the decimal either repeats or terminates. It can always be written as a,
Integer.
well, sometimes, but it can always be written as, what's ratio mean? Fraction. It can always be written as a fraction, right? So all of the rational roots, or the rational zeros, equal the factors of 12 divided by factors of 1 in this case. Okay, so how did I get those numbers? The rational zeros are always going to be built from a numerator that is a factor of the constant and a denominator that's a constant of the leading, that's a factor of the leading coefficient. So in this case, the leading coefficient is 1, so I know I'm getting a 1 on the bottom. Okay, a plus or minus 1. Factors of 12, well, how many integer factors of 12 are there? 12, 6, 4, 3, 2, and 1, right? So I would have to look at all of the fractions, positive and negative, with 1 on the bottom. That's convenient, so they're actually integers, right? Putting 1 on the bottom makes them integers. So the list actually was longer than what I gave you. It would have been plus or minus 12, plus or minus 6, plus or minus 4, plus or minus 3, plus or minus 2, and plus or minus 1. I only gave you the small ones. Now, if you were going to start from that list, how was the list you were starting with? What numbers would you want to plug in first?
The lowest.
The lowest ones. We're going to plug in the 1s first, then the 2s, then the 3s, because the big numbers are going to be more complicated. Okay.
If you enter the big numbers, that's gonna make your like the last, the little or the numbers on the bottom isn't
Well, it's going to tend to make them bigger, because if I'm always multiplying by a 12, for example, out front, when I get numbers, like if I had 5 on the bottom, 12 times 5 is 60, yikes. When I'm adding 60 up with other numbers, you see what I'm saying? It can get out of control pretty fast. So you want to start with the easy ones. The smaller the number is out in front of the synthetic box, the smaller the multiplication products are going to be, right? Now, how important is this? I would argue this is not very important because it only gives you the rational zeros. It doesn't say anything about the irrational zeros. Any square roots or cube roots or anything like that are not going to show up. And so it's honestly not that big a deal. It's not something that I really emphasize in Algebra 2 class. But there it is, right? Now, what you're going to, I might give you like 1 or 2 easy problems involving the rational root. But more than that, what I want you to be able to do is if you're given a list of maybe a couple potential zeros, can you whittle it down and see, which ones are and which ones aren't, and use that to write the polynomial in factor form. Okay? That's probably enough for one day, huh?
Yes.
Yeah.
Let's take a break.
All right, let's see here.
Hey, Mr. Boya,
Yeah.
would you want to do me a huge favor and fill this out for me?